Look across Egypt's western desert, and for hundreds of kilometers there is almost nothing but dry, barren ground. Then suddenly, there is water. A huge engineered channel cuts across the landscape. Beyond it, enormous green agricultural fields appear, where almost nothing grew before. But this is not a new natural river. At the heart of Egypt's New Delta project is a 174-kilometer conveyance route, built to collect and move agricultural drainage water toward one of the largest treatment systems of its kind. The route combines open canals, giant pipelines, hydraulic structures, and lifting stations. And the most surprising part is where the water begins. The project starts with water that has already been used once. Agricultural drainage water is collected from existing farmland, moved across the western delta, treated on an enormous scale, and returned to agricultural use. So how do you collect that much water, move it across 174 kilometers, clean it, pump it through the desert, and then turn barren land into working farmland? To understand that, we have to start inside Egypt's existing agricultural system. For thousands of years, Egyptian agriculture has depended on the Nile and the fertile land surrounding it. From the air, the contrast is unmistakable. The Nile Delta spreads northward as a broad green landscape filled with farms, canals, and cities. Move west, and that green begins to disappear. The land becomes increasingly dry. Beyond the established agricultural zone lies the western desert. Egypt's New Delta program was created to push large-scale agriculture into parts of that barren landscape. The overall development ambition reaches roughly 2.2 million feddans, an area measured in thousands of square kilometers. But land was never the hardest part of the problem. Egypt has enormous areas of desert. What it does not have in abundance is water. That means every attempt to create new farmland begins as a water engineering problem. Where will the supply come from? How will it reach the desert? How will its quality be controlled? And how can it keep arriving every day after the fields have been built? One important answer starts with agricultural drainage. When irrigation water reaches existing farmland, not all of it is consumed by crops. Some evaporates, some is absorbed by plants, some moves through the soil, and some leaves the fields through drainage systems. That drainage water has already passed through an agricultural environment. It may carry salts, suspended material, and other characteristics that make direct reuse more complicated. But it is still water. And in a country where every major new agricultural area increases demand, recovering part of that drainage flow can become extremely valuable. The New Delta system gathers water from 7 agricultural drains in the western delta and brings those flows into a larger collection and conveyance network. What begins as water spread across separate drainage channels is gradually concentrated into infrastructure capable of moving enormous volumes toward a common destination. This is the first transformation. Water that has already supported one agricultural cycle becomes the raw supply for another. But before that water can be reused, it has to travel. The main drainage water conveyance route stretches for about 174 kilometers, and the entire route is not one open canal. Roughly 152 kilometers are open channel sections. Another 22 kilometers are pipelines. Together, they form one connected transfer system. That distinction changes the engineering completely. Where an open channel is practical, large earthworks create a controlled hydraulic corridor through the landscape. Excavation establishes the channel geometry. Banks and embankments define the flow path. Hydraulic structures control water levels and movement. Crossings allow roads and other infrastructure to pass through the system. And along the route, engineers have to maintain a continuous hydraulic connection from one section to the next. But an open canal cannot solve every problem. In other sections, the water travels through large pipelines. Those reaches require a different construction process. Trenches have to be excavated. Large pipe sections have to be delivered, positioned, and connected. The pipeline must then transition back into the next hydraulic structure, or open channel reach. What is often described as an artificial river is actually a chain of canals, pipelines, hydraulic structures, and pumping stations. And simply connecting those pieces is not enough. Water naturally follows gravity. The new delta route could not rely on one uninterrupted downhill path all the way to its destination. At several points, engineers had to add energy back into the flow. The 174-kilometer drainage water route alone includes 12 lifting stations. At each of these locations, water approaches a new hydraulic step. Large pumping systems draw it in. Electric motors provide the power. The flow is lifted to the elevation or pressure needed for the next section. Then the water continues onward. Gravity may carry it through one reach. Another pumping station lifts it again. Then the process repeats. It is a staircase for water, and every step in that staircase requires energy. That makes the lifting stations part of the hydraulic backbone of the project. A canal can be perfectly excavated. A pipeline can be perfectly installed. But if the water cannot reach the required hydraulic level, the downstream system receives nothing, and the scale becomes even larger when the 174-kilometer route is placed inside the broader New Delta program. Official figures for the wider system describe 19 main pumping stations across the major water routes serving the development. So this is not a project where water is simply released at one end and allowed to find its own way across the desert. Its movement has to be engineered. But transporting agricultural drainage water only moves the problem. It does not solve the question of water quality. That requires treatment. At the end of the major collection route sits the New Delta Treatment Complex. Its design capacity reaches up to 7.5 million cubic meters of water per day. Day after day, agricultural drainage water can arrive at an industrial facility built specifically to prepare that flow for another cycle of irrigation. This is not a seawater desalination plant. It is not taking water from the Mediterranean and turning it into drinking water. Its purpose is different. The agricultural drainage water undergoes large-scale advanced treatment before being returned to irrigation use. At this scale, the treatment complex becomes an enormous piece of agricultural infrastructure in its own right. Incoming flows have to be distributed through treatment facilities. Pumping equipment keeps water moving. Large process areas operate continuously. And treated water has to leave the complex at a rate compatible with the agricultural system downstream. That is why the canal is only the visible part of the project. Behind it is a water reuse machine, and even a plant capable of treating 7.5 million cubic meters every day does not supply the entire New Delta on its own. That distinction is critical. The broader agricultural development depends on several water sources. Treated agricultural drainage water is one major component. Surface water connected to the Nile system contributes through other infrastructure. Groundwater also supports agriculture in some areas. The 174-kilometer route is therefore only one part of the larger New Delta water system. That larger system has to combine water from different sources and then deliver it to agricultural zones spread across an enormous area. And getting water to the desert is still not the same as getting water to a crop. Once the main supply reaches the development area, the flow has to be divided again. Large regional routes feed smaller distribution systems. Channels and pipelines carry water towards separate agricultural blocks. Control structures regulate how much flow enters each section. Additional pumping may be required where elevation or pressure demands it. And eventually, a flow measured in millions of cubic meters per day becomes thousands of smaller supplies feeding individual farms. This branching network is what turns regional water infrastructure into agriculture. Without distribution, the main canal would simply pass through the desert. But even when the water arrives, a desert is still not a farm. Land has to be prepared. Large areas must be surveyed and graded. Access roads have to reach fields and pumping equipment. Agricultural blocks need irrigation layouts. Water connections need to be installed. Drainage has to be considered. And field geometry has to match the irrigation system that will operate there. This is where one of the most recognizable features of the New Delta begins to appear. Center pivot irrigation. From ground level, a center pivot is a long steel structure supported by wheeled towers. Water enters near a central point. The structure extends outward across the field. Sprinklers distribute water along its length, and the entire machine slowly rotates around the center. One rotation irrigates a circular area. From the air, the result is unmistakable. One green circle appears against the desert, then another, then dozens. Eventually, large sections of previously barren land become patterns of circles and rectangular fields. But every one of those green shapes depends on an invisible chain extending far beyond the farm. A drainage channel in the old delta, a collection system, a lifting station, an open canal, a pipeline, a treatment complex, another water route, a distribution network, and finally, the irrigation system turning above the field. The farms are the end product. The real machinery is the system behind them. Water alone also does not instantly transform desert ground into productive agriculture. Fields have to be managed. Crops must be suited to local conditions. Irrigation has to be controlled. And drainage remains essential. In an arid climate, irrigation creates another problem that is easy to overlook: salt. As water is applied and then evaporates or is taken up by crops, dissolved salts can remain behind. If drainage and water management are poor, those salts can accumulate in the root zone and reduce agricultural productivity. So the same project that has to bring water into the desert also has to prevent that water from gradually damaging the soil it is supposed to support. That is why treatment, drainage, crop selection, and irrigation control matter long after construction crews have left. From the air, however, the transformation is extraordinary. Satellite imagery over recent years shows agricultural development spreading through areas west of the old Nile Delta. Where much of the landscape once appeared uniformly barren, geometric agricultural blocks now occupy increasingly large areas. The new Delta program ultimately targets around 2.2 million fedans. That does not mean every part of that target area is already completely cultivated. The project covers an enormous development zone, and large areas of desert remain visible around the farms. But that contrast is exactly what reveals the engineering. The climate has not suddenly changed. Rainfall has not created a new river. The surrounding desert remains dry. The green fields exist because water continues to arrive through infrastructure. And that means the project never truly reaches a point where the water problem disappears. Every cultivated hectare becomes another long-term demand on the system. Pumps must continue running. Treatment equipment must remain operational. Canals have to be maintained. Pipelines have to remain intact. Distribution structures have to keep delivering the correct flows. And this brings the story back to energy. At millions of cubic meters per day, even modest elevation changes translate into enormous pumping requirements. The broader New Delta program therefore required electrical infrastructure on a massive scale, with official figures citing roughly 2 gigawatts of supporting generating capacity. That does not mean every pump constantly consumes 2 gigawatts, but it shows the scale of the energy system built around the wider development. This is why New Delta cannot be understood as only a water project. It is also a pumping project, a treatment project, a power project, a land reclamation project, and an agricultural project. All of those systems have to operate together. Groundwater adds another layer of complexity. It can provide an important additional source in parts of the development, but groundwater conditions are not identical everywhere. Recharge and sustainable yield vary from one aquifer to another. Long-term expansion, therefore, depends on monitoring how quickly groundwater is being removed and how those reserves respond over time. The same is true for drainage water reuse. Recycling water improves the productivity of the available supply, but reuse does not create unlimited water. Quality still has to be managed. Salinity still has to be controlled. Treatment requires maintenance, and every pumping step consumes energy. That is the real scale of the New Delta challenge. From the air, the project can look almost simple. A blue channel cuts across golden desert. Green circles spread beside it. Crops grow. But the visible canal is only one link in a much larger engineering chain. The 174-kilometer drainage water route collects flows that have already passed through existing farmland. 12 lifting stations help move that water across the route. Open channels and pipelines carry it toward treatment. A facility capable of handling millions of cubic meters every day prepares it for reuse. The broader network combines that supply with other water sources. Distribution systems spread the flow across the desert. Land is prepared, center pivots turn, and eventually, barren ground becomes working farmland. Egypt has shown that engineering can create agriculture where no natural river crosses the landscape. It can recover water that has already been used. It can lift that water against the terrain. It can transport it through canals and pipelines. And it can build an agricultural system around that supply. But making the desert green once is not the final test. The real test is keeping it green year after year. While the water remains available, the pumps keep running, soil salinity stays under control, and every part of the system continues working together.